Thank you, Professor Umera, for your very engaging talk. And your talk has provided us with a very insightful overview of this morph-assisted preparation of polymers with some very exciting properties and applications. We have a lot of questions coming in. And before proceeding to these questions, let me take this opportunity to thank Dr. Sharmishta Das, my co-moderator, for compiling all these questions for us. So without further delay, let me jump into the questions right away. So the first question that came in was, how do you select these morph scaffolds for a specific polymerization reaction?
Okay, so we okay, of course we have many choices, and the most important thing is so we have to think about the polymer thickness, and then actually, so that means the size of the morph channels is very important to regulate the polymerization. If the size of the of channel is smaller than the polymer thickness, of course, we cannot include the monomers, and we cannot include the polymers here. So the size of the polymer thickness and the morph channel is very important.
Right. In a connected note, is there a role for these morphs other than, is it just limited to the spore size, or like are there other factors or other influences?
Yeah, so it depends on the how we want to regulate the polymerization. So if we want to prepare some kind of a chiral polymers, so we can prepare the chiral morphs. And we want to perform the, so the 2D networks. So we have to choose the 2D morphs. I mean the pillared layer type of morphs. And we use the 3D type morph networks. And we incorporate the monomer and the cross-linker together. We can obtain the cross-linked polymers inside the morphs. So poor dimensionality is also the important factors.
Okay, thank you. On a related note, are there any like specific features for these morphs like porosity, stability, or specific metal or functional groups?
Yeah,
That will allow this insertion.
Of course, stability is also important. But after, after the polymerization, so that we have to isolate the polymers. So of course we can isolate the polymer just by washing to isolate the polymers. But sometimes it's tough to obtain the polymers quantitatively. But so the morph is a coordination compound. So so if we dissolve in the chelating solution, we can isolate the polymers quantitatively. We can digest the framework. So stability depends. So the high stability is necessary for the polymerization. But if the stability is very high, it's quite difficult to isolate the polymers. But so for the polymerization of the carbon polymers, so I show the example of the polyacenes of the or other GNRs. So in that case, we for the polymerization, we heated the composite at very high temperatures, over 300 degrees C. So in that case, we need more with higher thermal stabilities, of course.
So you were talking about like this oriented morphs. So what is the preparation method you generally prefer for preparation of these oriented morphs? Is it difficult to attain such morphs?
So to prepare the morph with high thermal stability, we often use the zirconium morphs because that kind of the morph is high thermal stabilities. But so of course it depends. So to choose the metal is depends on how we perform the polymerization. And then okay, and for example, in the last topic, I just showed the example of the polymer recognition using the unsaturated site in the MOS. In that case, we use the iron MOS because iron can coordinate to the polymers or monomers. So yeah, we often use the copper or cobalt to interact with the polymers or monomers. But when we use the zinc MOFs, so zinc do not interact the monomer or the polymers effectively. So yeah, we don't care about that.
So another question we had is about like, how do you ensure that this polymerization proceeds within this MOF structure? Do you use the same stoichiometric amount between the monomer and the MOF? And how do you make sure that this process is happening?
Yeah, first thing is that we check the XRD. And the XRD pattern is not changed before and after the polymerization. That means that the polymerization does not destroy the frameworks. Then, if a polymer is located accommodated inside the MOFs, XRD, so some kind of shift of the XRPD is observed. So this is one evidence. And we also perform the adsorption measurement, gas adsorption measurement, before and after the polymerization. So the when polymer is accommodated inside the MOS, of course, the capacity of the gas adsorption is decreased. And the direct evidence is obtained from the solid state NMR measurement. So we can observe the both peaks for the MOFs and also for the polymers. But it's only applicable for the MOFs with the non-magnetic metals.
Yes,
Because
yes.
magnetic metals, so they cannot be applicable for the NMR measurement. Yeah.
Right. On a related note, like if I understand correctly, you use some of the solution step to remove the MOF and isolate this polymers. So, do this step has some detrimental effects on this polymer properties or composition, especially in case of polymers with single molecular thickness?
It depends. It depends. So mild condition is better to isolate the polymers. And if we use, we can also use the acid or base to isolate the polymers. But if polymer is, not stable in the acid or the base, so it's not good. So it depends on the polymers, yes, used.
While we are on the topic of this MOF dissolution, um, so we are dissolving this MOFs to obtain this free polymer. So does this imply that these MOFs are of single-use system? Is it possible for we can recycle or reuse this MOFs?
Right. Yeah, it's also a good question. So basically we can wash the composites to isolate the polymers. In that case, we can recycle the MOS to be polymerized, to perform polymerization again. But if we digest the framework using the acid or base, so after collecting the solution, we can neutralize to recover, to synthesize the MOF again. Then we can do the synthesis of the polymers inside the MOF again. Yeah, so basically we can recycle this system.
Sorry to pitch in. Due to paucity of time, we can take a couple more questions. I understand there are so many questions lined up. So, Reshmi, please choose two of them.
Yeah, sure. Another question that came in is about the potential of industrial translation of these techniques for the preparation of polymers.
Yeah. So now we can, of course, scale up this system, and we perform the gram scale reaction synthesis of the polymers inside the MOS. So I hope we can scale up this system and we can apply this system for the industries, for the synthetic system. But in the second topic today, so I talked about the separation. In that case, of course, we can prepare the MOS with several tens gram or ton scale right now in the industry. So in that case, we can apply this system for the industry, I think, for the polymer separation system or recognition system. So I think it's promising.
One last question. Could you also comment on how these techniques stand environmentally compared to all these traditionally available synthesis techniques?
Oh, so yeah, I think to regulate the polymer structures. So this system is really nice, but the most, I think the biggest problem in this system would be the cost, I think. Yeah, we use more, so we have to use more, so more cost. So cost is the problem, I think.
So before we end, as we are running out of time, before we end this session, could you please share some concluding remark for all our participants?
Okay. Yes. Thank you very much for the kind attention on my talk. So I'm really happy to share my work with many colleagues in the world. Thank you very much.